il video, il laptop, il tablet?
Sì, tutto a posto. Vai quando vuoi.
Okay. Good morning, everybody. Today's lecture is entitled The Very Tricky Longitudinal Correlation, also known as the Soralella discussion, even though only 2 of you in the audience can get this. Anyway, so we've seen the last time that the scale-free correlations of the velocity fluctuation of natural flux seems not to need any particular biological tuning to be explained, as they are quite naturally the consequence of the spontaneous breaking of the continuous rotational symmetry of the flux. So in other words, a flock has potentially infinitely many directions along which to fly. It will select one direction spontaneously, so it will break the symmetry. So there is continuous spontaneous symmetry breaking. And this creates a Goldstone transverse massless mode. And because we've seen that the mass is intimately connected to the correlation length, this results implies that the correlation length of the velocity fluctuation should indeed scale linearly with the size of the system. Okay, so in this respect, our first conclusion was that that result was nothing particularly spectacular from the biological point of view. It was just a consequence of this piece of theoretical physics. However, Goldstone modes, the transverse modes, was not the only kind of fluctuation we had in the theory. So let us go back to our Hamiltonian. And once we had expanded the Hamiltonian around the Landau ground state and see what was the form. So integral in ddx, 1/2 the gradient of the 2 kinds of fluctuations. So gradient of delta phi perp square. Okay. Then we had 2 modulus of mu square delta phi longitudinal square plus the non-Gaussian part. We'll come to the non-Gaussian part later, but for the moment, the important thing is that we do have a massive mode. This guy here, the longitudinal fluctuations, they do have a non-zero mass, right? So the mass of the longitudinal fluctuation, which is twice the modulus of the original mass of the theory, is different from 0. So this means that the longitudinal correlation length should not be infinite in the theory. Okay, so the transverse fluctuations are massless, but the longitudinal fluctuations should be massive, so with a non-infinite correlation length. However, remember that this is in principle only true at the Gaussian level. Okay, so what do experiments say about that, right? So if we go back to our experimental data, what can we say about that? Okay, so what are the longitudinal fluctuations? So let's go back to our representation. Okay, so this phi naught here, the symmetry broken state. So phi naught represents the overall direction of the flock. So this is the longitudinal direction. This is the orthogonal direction. So a delta phi longitudinal, so this piece here, certainly changes the modulus of the field. Okay, so delta phi changes the modulus of phi. Okay, but we did measure the fluctuation of the modulus of the velocity in the birds, because the modulus of the velocities, modulus of the VI, is simply the speed of the individual birds. And in our data, we did measure, remember from the first lecture, the speed fluctuations and the speed correlations. So speed fluctuations in real flock, we can define the speed. So let's call the speed SI, so the modulus of VI. And then we define the space average fluctuation. So delta SI is equal to the speed of bird I minus 1 over n sum over k of the modulus of Vk. Okay, so this is the speed fluctuation. And so we can then compute in the standard way the speed correlation function. So delta Si, delta Sj, we can measure this as a function of the distance between I and j in the way I explained the other lecture. So we have a correlation function of the speed as a function of r. And from this, we can extract the speed correlation length. Okay, so how does this look like in real flux? Well, psi of the speed as a function of L is still very, very much linear in the data. So the speed correlation length is also scale free. So then this maybe is surprising because, so what do we have? So we have the biological level telling us that the speed correlation length, if we were in the bulk, would be infinite. So we are not in the bulk, we have a finite system, but let me make an abuse of language here. So if we were in the bulk, would be infinite, so it's a scale free, okay? But we've just seen from the physics outside that the longitudinal fluctuations, so the longitudinal correlation length, should be finite, okay? And this is, remember, simply because this is the symmetry broken potential. If you select one state, so this fluctuation, the fluctuation that brings you up and down this hill are massive. They cost you energy. So the question is, are we finally in front of some interesting discrepancy between the biological result and the physical result? So is this really interesting? So should we really now find some biological mechanism to explain why the speed correlation length is scale free, when on the other hand, in the physical case, the longitudinal correlation length is finite? Well, I'm afraid we're not still there, because the answer to this question is tricky and we must be very, very careful. So the fact is that this result, the fact that the longitudinal mass is different from zero, so that the longitudinal correlation length is finite. So this result is only true at the Gaussian level. This means that when you take into account the non-Gaussian parts of the Hamiltonian, and you compute the actual or renormalized longitudinal mass, so the real correlation length in the theory, you find a different result. What you find is, if you take into account the nonlinear part, so by taking into account the non-Gaussian part, so what is called the interaction, what you find is that the renormalized mass is also zero. So this is the renormalized mass. So the true mass of the theory, so that the actual longitudinal correlation length is also infinity. And then in a finite size system, yes, you would get that psi longitudinal scales with L, right? As for the speed in flock. So it seems that they were back to square one, so that even the scale-free speed correlation in flock are due to some physical result, okay? So this is surprising. I will give you, well, the lecture today will be devoted to the discrepancy between these two results, the Gaussian result and the interacting result. So the fact that the longitudinal correlation is a very sneaky object, which is actually scale-free as well when you take into account correlation. But before we go into that, let me make a table, because this may be very confusing for you at the moment. So here we have the Gaussian level, so also called the bare or tree level, okay? Here we have the non-Gaussian level, so the real theory or renormalized. So transverse mode. Okay, so the transverse bare mass is equal to 0. So this is the Goldstone theorem, okay? But also the renormalized bare mass stays 0, meaning that the transverse correlation length is infinite, right? So the system is scale-free. And remember, this happens because this result is word protected. So it's protected against renormalization by the word identity, the word Takahashi identity, okay? On the other hand, the longitudinal mode is more problematic because the bare mass, so the Gaussian level, is different from 0. However, the renormalized longitudinal mass is equal to 0. So the longitudinal correlation length is infinite. So it's scale-free. And so maybe this is the explanation of our results, maybe not, we will see later, but certainly the situation is more complicated than what we expected. Okay, so why is that? So this seems surprising because if you go back to the usual drawing of the potential that we did for 1,000 times, so let's do it again, of the Mexican hat, it really seems very natural and very true that the fluctuation carrying you uphill of the potential, which are the longitudinal fluctuations, are massive, and so they should cost energy. So it's very unclear why the correlation function of that should be scale-free. Okay, so it's really a result we would like to explain. Okay, I will give you two arguments for explaining this result, two different ways. The first way is a diagrammatic argument. I will only go through it very well as few details as possible, because maybe not all of you have the background to get this perturbative diagrammatic argument. But I want to give it to you because it's interesting to see how even quite technical details of theoretical physics are actually needed to fully understand some biological results. So the first argument is the diagrammatic one. So diagrammatic explanation of why m longitudinal is equal to 0. So because we said that this is something due to the interactions, to the non-Gaussian part of our theory, so let's finally see what was that non-Gaussian part. So here you have the gradient square of the fluctuations plus the mass of the longitudinal, the non-zero bare mass of the longitudinal fluctuations. But now what is interesting for us is the interaction, so the non-Gaussian part. So we have the cubic one, which is delta phi longitudinal times delta phi longitudinal square plus delta phi perp square, plus lambda delta phi longitudinal square plus delta phi perp square, everything square. So we see that there is a curious term here, which is this one, when this piece couples with this other piece. Because this is the lowest order term which couples longitudinal and transverse fluctuations. So that is a term, delta phi longitudinal times delta phi perp squared. So is what we normally would call in field theory a cubic vertex, which is coupling longitudinal and transverse fluctuation. So if we want to give a diagrammatic expression for, well, a diagrammatic representation for it, well, we can assign a line to the longitudinal field, a dotted line to the transverse field. And so that object, so the delta phi longitudinal, delta phi perp square, diagrammatically is something like that. Okay, so this indicates delta phi longitudinal, delta phi perp, delta phi perp. So this is a very intriguing object, this kind of vertex, because, well, if we were particle physicists, we would be tempted to say that the massive longitudinal particle, because remember at the bare level, this guy here is massive, that the massive longitudinal particle decays into two massless transverse particles. So then maybe the original massive longitudinal particle maybe is not a real particle after all, it's just a resonance. This would be the approach of a particle physicist, but we're not particle physicists. So let us just use this vertex to calculate the correlation function, the longitudinal correlation function, by using some standard diagrammatic expansion and at the lowest order, so at one loop. So we want to compute delta phi longitudinal, delta phi longitudinal, okay? So diagrammatically, this means putting together two lines field, okay? So this and that, this is the delta phi longitudinal. So at the lowest order, of course, you just have these two fields. But if you go on expanding the Hamiltonian, then you will have the vertex, the cubic vertex. So you find a term like that in which two, sorry, we can avoid the arrows because we don't need that. So you can put two cubic vertex in front of each other, right? So this is delta phi longitudinal, delta phi perp, delta phi perp, delta phi longitudinal, okay? So now you have to connect these lines. There are many ways to connect, but I want to focus on one particular way to connect it. So this equation, we can rewrite it diagrammatically saying that the full correlation function G parallel longitudinal, it's equal, okay, if we connect these two, we just have the bare, the Gaussian correlation function of the longitudinal modes, okay? And if we connect now these lines here, we get a diagram like that. Okay, so this gives rise to a longitudinal correlation function. The external one on the right is also longitudinal correlation function. But you see that now inside the bubble, inside the diagrams, you have connected transverse field. So this gives rise to some transverse correlation function. The knot here means the correlation function at the Gaussian level. This is what always happens when you do diagrammatic perturbation theory. You write the full correlation functions as in terms of combination of the Gaussian correlation function, the expression of which you know exactly. If we do this calculation in K-space, and you always do renormalization and diagrammatic expansion in K-space, in Fourier space, so this would be the correlation function computed at the momentum K. So here you have K. On these external legs, you have K. Well, on the internal legs, you have to know a little bit of of Feynman rules, but you have one loop, so one integration of one internal momentum. Let's call it Q and put it on that line. And then because of momentum conservation on this other line, you get K minus Q, okay? So now what are the bare correlators of the theory, the one that we will be using to compute this perturbation series? So the bare correlations, that is the Gaussian, sorry, bare and Gaussian is the same thing. So the longitudinal one, we know, is just the inverse of the quadratic part of the longitudinal field, which is k squared plus mu longitudinal square, because remember, mu longitudinal at the Gaussian level is different from 0. On the other hand, the perpendicular correlation function is just 1 over k squared. Why? Because the perpendicular mass is equal to 0. By the way, it's also equal to 0 at the normalized level, but this is not important for us now. Okay, so these are the two objects I have to put into that diagram, okay? So now if I read the expression from the diagrammatic one, I say that the full longitudinal correlation function is equal to the Gaussian longitudinal correlation function plus I have this external legs, and then I have an integral. So one loop, it means one integral on the internal wave vector delta k, sorry, ddq, and then you have 1 over q squared for one of the two transverse correlation function, and 1 over k minus q squared. And then you have the other external leg. Sorry, I see that this choice of variables have been very confusing probably. So let me write directly the bare propagators as a function of the generic momentum p, right? So you will not confuse. So this is p squared, and this is 1 over p squared, okay? So in this case, on this line here, p is equal to q. On this line here, p is equal to k minus q. Okay, so this is an important result, because what you get is that the perturbative expansion of the real longitudinal correlation function contains integrals of the perpendicular correlation function. So the correlations are coupled by this expression, and this is a game changer. Why? Well, let's compute something which is easily connected to the correlation function, even more easily connected than the correlation length, which is the susceptibility, chi. So the longitudinal susceptibility. Well, in general, and this, you should go back to good old statistical mechanics, but the susceptibility is simply the correlation function in k space evaluated at k equal to 0. This is a general relation when you have an equilibrium distribution. It comes from the fact that the susceptibility is the space integral of the space correlation function. So when you go to Fourier, the space integral is simply the value k equals 0 of the correlation function, okay? So what is this? Okay, so the first piece at k equal to 0 is 1 over mu parallel square, right? Plus, and then we have two of these guys outside, so we group them together, is 1 over mu parallel fourth. But then I have the integral over d dq, and then if I put k equal to 0, I have 1 over q fourth. So now let's be careful, because if the system is infinite, so if you are in the bulk, the lower extreme of integration here is 0. So the infrared extreme of integration is 0. On the other hand, the upper degrees of extreme of integration is some cutoff lambda, which is large but finite. So we don't care about ultraviolet divergence here. So the important point is this 0 here, okay? Because now you see that if d, the dimension of space, is low enough, this integral is divergent for small q. So you have an infrared divergence for low enough d, right? So infrared divergences in critical phenomena are always due to collective phenomena. So infrared means small wave vector, so small q. Small q means large distances, large r. So infrared divergences are typically those contributed to all the critical divergence in critical phenomena. So this is telling us that this piece here is diverging at low enough dimensions. So this first piece here, the 1 over mu parallel square, well, this is simply the Gaussian longitudinal susceptibility, which is finite because the Gaussian mass is non-zero. But these other terms, the integral, because it contains the transverse correlation function, is diverging. And in fact, what you can see is that chi longitudinal is infinite for d smaller than 4. And this 4 clearly comes from this 4 here, right? In particular, because we know that also the transverse susceptibility was diverging, okay, you get a general result with telling you that the longitudinal susceptibility is equal to the transverse susceptibility to the epsilon over 2, where epsilon is the famous or infamous 4 minus d of the epsilon expansion. Well, if you did that at school, but never mind the epsilon expansion. So epsilon is just 4 minus d. So this means that, for example, in 3 dimensions, which is the one of interest for us, the longitudinal susceptibility goes like the transverse susceptibility to 1/2. So it's still divergent. It's a weaker divergence, okay? So this, the fact that it is a weaker divergence is connected to the fact that actually you have this uphill fluctuation that seem massive, but they're not. So longitudinal and transverse modes are so strongly coupled in the theory to each other that the divergence of the transverse susceptibility, which I remind you is protected by the word identity, inevitably implies the divergence of the longitudinal susceptibility. And because psi and chi are connected intimately, so if chi longitudinal is equal to infinity, then clearly also the longitudinal correlation length, it's infinity, which means that in finite systems, scales with L. Okay, so this was due to this diagrammatic argument, which is probably not particularly enlightening for some of you. I think it is interesting because directly you get immediately suspicious when you see this kind of vertex in the theory. So you don't have to apply any particular argument to say, there's a vertex coupling the two fields, so bad things can happen, and actually bad things happen, right? So let me give you a more, what I hope is a more intuitive argument of the same result, which is a geometric argument. And this should be easier to grasp. So geometric argument for m parallel, so the renormalized longitudinal mass being equal to 0. Okay, so remember, we have written, so given our, now we can say, little deceptive scheme, right? So we have called this phi naught, this is the longitudinal direction, this is the transverse direction, and we wrote a generic field phi as phi naught plus a longitudinal fluctuation and the transverse fluctuation. Okay, so now look at that. Let me take a new field phi different from phi naught, which has exactly the same modulus as phi naught. So this is phi. So you see that in this case, of course, you do have some transverse fluctuation. Okay, so this is delta phi Perp. But what is important is that you also have a longitudinal fluctuation. This piece here, well, it's smaller than that, so it's just up to the circle. So this piece here is a delta phi longitudinal. So this is very important. You see that with this representation, a rotation theta that does not change the modulus of phi still creates a non-zero delta phi longitudinal. So let's write this down. So a rotation that does not change the modulus of phi still entails a delta phi longitudinal different from zero. So you see that clearly our identification of the longitudinal fluctuations with the modulus fluctuation was a bit bogus, right? So in this case, when the modulus is constant, if we take a fluctuation which is just a rotation, what are the two fluctuations? The perpendicular one is phi naught times the sine of theta, of course, that for small theta is phi naught theta. And what is delta phi longitudinal? Well, delta phi longitudinal will be phi naught 1 minus the cos of theta. This is this purple bit here. And this goes like phi naught times theta squared over 2. So you see the longitude, the transverse fluctuations are basically the same as theta. And theta is the parameter of the symmetry. The longitudinal fluctuations are smaller than that because it's a theta square, but still not zero. So the problem is that we've chosen a representation, delta phi perp, delta phi longitudinal, that is not diagonal in the symmetry. So the parameter of the rotation, which is theta, so theta is really what parameterizes the symmetry, in this case, the rotation. So the parameter of the rotation enters in both the fluctuations, not just one of them. So the bona fide, the true Goldstone mode is theta. So that is the true massless parameter, right? And theta is linearly connected to delta phi perp, so it's okay to say that the transverse fluctuations are the zero mode because theta and delta phi perp are basically the same thing. But theta also enter in delta phi longitudinal, even though at the second order. So that the massless nature of theta contributes also to the correlator of the longitudinal delta phi. And this is why the longitudinal psi diverges. So let me try to give a more physical argument, well, try to do an even more physical argument for that. So let's go back to the microscopic theory for a minute. So in the microscopic theory, imagine that you have a fixed modulus, phi I, modulus of phi I equal to 1 for each I. So this is not our theory. Remember, we have that the microscopic speed fluctuates in birds. So I'm just making a diversion now to something else. So this is a theory like the Heisenberg, the classical Heisenberg ferromagnet, if you want. So each one of the small arrow has fixed modulus. Okay. So once you do the coarse graining, so now we do the coarse graining. So the coarse graining is what? Well, you take a small volume in space, right? And you average all the little arrows in that small volume. So once you do the cross graining, due to small fluctuations, because remember, you are at low noise, but not zero noise. You do have some small fluctuations in the directions of motions of this guy. So due to the small fluctuation, the modulus of the field will be slightly smaller than 1. So in this volume, all the arrows will be more or less everybody up. So if this is the overall direction of motion, up. But the small fluctuations will give you a field, so phi of x, whose modulus will be smaller than 1. So the field will be some local average, so 1 over, I don't know, the number of particles you have in that box, sum over I of phi I. And even though each individual microscopic arrows are modulus 1, because you're summing the vectors, this will be smaller, perhaps close, but something smaller than 1. Okay? So now let's go to the Perp and longitudinal representation. So let me put all my arrows on a line. Okay. So this, the vertical lines, is really the spontaneously broken direction. So this is the longitudinal direction. Okay, so everybody is going up, but with small fluctuations. So this guy, so this is the average direction. So this guy will go in this direction, perhaps. So also this guy in this direction, this guy a little bit to the left, and so on and so forth. So there will be random fluctuations around the direction of motion, so that the average is up. Okay, and again, all of them, all the microscopic degrees of freedom, they have all the same modulus. So now add a longitudinal field. So a field which is really pointing along the spontaneously broken direction. And let's ask ourselves, what is the effect of this longitudinal field? So I'm putting an external field exactly in the same direction as the overall direction of the order parameter. So in the same direction of the direction of motion. So what is the effect of this? Well, you see, because all the microscopic arrows have the same fixed length, the effect of the field cannot be to change the individual microscopic modulus, because that is fixed. Okay, so you cannot change the length of the arrows. But what they can do is now to align more along the longitudinal field. And this is exactly what they will do. So what they will do is that, okay, so now there is, yes, I had fluctuation, but now there is a strong, or even not strong, there is a field in the longitudinal direction. So what they will do will be to rotate in such a way to align along the direction of the field, okay? So now they have rotated. So let's say, and now all go really up because of the field. And this rotation is the one which excites the theta mode, the transverse mode. So you see, by doing that, you're really exciting the fluctuation of theta. So, of the transverse mode. So in practice, you are changing, you're increasing the longitudinal component of the total field, because clearly now the total field will be larger, right? Because they're more, or everybody is more aligned than before. The direction is exactly the same. So I have increased the longitudinal order parameter. So I have increased the modulus of the order parameter by just rotating the microscopic degrees of freedom. So this is why you have this strong coupling between the two. So you can actually act on the longitudinal mode by simply rotating the fields. Okay. So then what is going on here? It seems that everything is totally scale-free in this theory. So that there is absolutely nothing which is massive and not scale-free. It seems strange. So let's write this question down. So is then everything scale-free? Because we saw that the transverse mode are scale-free. Now the longitudinal modes are also scale-free. So what's going on? Is it everything really scale-free? Well, no, of course not. We simply have to be careful and use a representation, a coordinate systems, if you wish, that is truly diagonal in the symmetry. And so we go back to the spoiler of Chiara of yesterday. So not everything, not every, so let's say not every fluctuation is scale-free. If we go polar, so if we use a polar representation, we see this very well. So the polar representation means, okay, forget about transverse and perpendicular, use the good old rho and theta representation. Okay. So, but now rho and theta are fields, okay? So you have a rho of x, the modulus field, which will be some symmetry broken, the modulus of the spontaneous symmetry broken of the parameter, plus some fluctuations. And similarly, theta, field theta, will be some theta naught plus fluctuations. Okay, so it's the same, apparently the same scheme, with a big difference. So if this is your phi naught, okay, so now when you have a generic phi, you have a fluctuation of the angle delta theta, and you have an independent, an uncoupled fluctuation of the modulus delta rho. So, well, this is the case where theta naught is equal to 0. Okay, because we're putting the phi naught along the x-axis. Okay. So the very important things of this representation is that delta rho and delta theta are now decoupled within the rotational symmetry. Okay, so the symmetry moves theta, of course, because theta is the parameter of the rotational symmetry, and not, it doesn't move rho. Okay, so delta theta different from 0. Before, you see, you remember, it would create a delta phi longitudinal different from 0, but now the delta rho stays 0 when you rotate. So this is the crucial difference with respect to the previous representation. So this was our mistake. The transverse mode is indeed the same, quite the same as the Goldstone mode delta theta, but the longitudinal mode is not, because it's not the mode orthogonal to theta and to Perp. Okay, the longitudinal mode is a hybrid mode, which is coupling delta theta and delta rho. So now, if you go back to the expansion of the Hamiltonian, now you make an expansion in terms of delta theta and delta rho. Okay, I will not do that explicitly, but you can do that yourself, is that you do not find any vertex of the kind delta rho times delta theta square. So that is not there. Okay, so even at the level of the Hamiltonian, the two fields decouple, which is of course to be expected, because remember the Hamiltonian was symmetric, was invariant under the rotation. So if you use the correct representation of the rotation, so the correct parameter theta, and the variable which is actually orthogonal independent from it, then the Hamiltonian, which is invariant under that rotation, will not couple the two fields. Okay, so in H, okay, delta theta and delta rho are decoupled. And unsurprisingly, in the expansion of the potential, what you will find, well, you will find exactly the same mass as the longitudinal, the bare longitudinal one for delta rho square, okay, plus the non-Gaussian terms, right? So you have that mu rho square is different from 0, okay? You have that mu theta square, of course, is equal to 0. This is the Goldstone mode. And because they are decoupled, there is no way for the theory to build a correction to the mass of rho by using the mass of theta. So because they are decoupled, so delta theta and delta rho are decoupled. So decoupled in H. So there is no way in which the fluctuations of theta can change the mass of rho. So what happens then is that even the renormalized value of the modulus mass will be different from 0. While we know the renormalized value of the Goldstone mode will be equal to 0 thanks to the Ward-Takahashi identities. So finally, we have our massive mode. So let's then update the table that we did before. Okay, so this is the Gaussian case or free theory, and this is the non-Gaussian. So this is also called the bare level, and this is the renormalized. So now we have a different pair of modes. So the delta theta is the Goldstone mode, is Gaussian mass is 0, its renormalized mass is also 0, and the modulus mode. Mu rho is different from 0, and m rho is different from 0. So this means then that the correlation length psi of theta, which is however basically the same of psi perp, which is also very much the same as psi of the velocity fluctuation, will be infinite, while the psi of the modulus fluctuations, that must be finite. So we finally found our massive particles. This is our massive particle. So it's the modulus fluctuations. So let me, before we go back to flux, because I have time, I see, let me indulge a bit on on this result, which I think is very nice. And let me go back to the coupling between the transverse and the longitudinal mode, because it still seems strange that the longitudinal mode is completely different from the modulus mode. Well, it's not completely different, okay? It contains both of the modes, and now we'll see how. So let me go momentarily back. So back to transverse versus longitudinal. So the full field phi now, we're writing that as rho cos theta, rho sine theta, okay? So, but rho is equal to rho naught plus delta rho, and theta, let's say that is 0, so let's take 0 as a reference point plus delta theta. So theta and delta theta are the same. Okay, so we put that into that expression. So we have rho naught plus delta rho times 1 minus 1 alpha delta theta square. We have expanded the cos time, and rho naught plus delta rho times delta theta. We have expanded the sign. Okay, we make these products. So we get rho naught minus rho naught delta theta square over 2 plus delta rho naught delta theta plus delta rho delta theta. So, okay, so this reconstitutes the phi naught. Remember, phi naught is simply components rho naught 0, okay, plus delta rho minus rho naught delta theta square over 2, rho naught delta theta plus delta rho delta theta. And this is what we wrote with the former representation as phi naught plus delta phi longitudinal, delta phi perpendicular. So now we have the expression of delta phi longitudinal and delta phi perp, the full expression, as a function of the fluctuation of the diagonal fields, rho and theta. So how are they? So we have the delta phi longitudinal is delta rho minus rho naught delta theta square over 2. And delta phi perp, it's equal to rho naught delta theta plus delta rho delta theta. So let's look at this expression quite with attention. So you see the longitudinal degree of freedom is indeed proportional at first order to the modulus fluctuations. So it is there, that contribution. However, there is a second order contribution, which is this guy here, which will contribute clearly to the correlation of the longitudinal. But you may say, but come on, that is of the second order, it's much smaller. So given this, I could expect that at first order, the longitudinal fluctuations are really the same as the modulus fluctuations. Well, in a way they are, but the problem is the correlation function. So let's see how this representation impacts on the correlation function. So because we know that delta rho is certainly massive, okay, the correlation function of delta rho, C rho, sorry, I'm switching from C to G for the correlation function. I'm sorry, they are the same. Is that in stat mech we tend to use C, in particle physics we tend to use G for the propagator, but never mind. If you look at your notes, they are the same. C and G, they are the same. So then the correlation function of the modulus will certainly have an exponential part, e to the minus r over xi to the rho, sort of short range, right? There may be some power law correction, but the important point is that because it is massive, because it has a finite correlation length, there is an exponential decay, or maybe some other function is a short range function. While theta is the Goldstone mode, so no mass, so infinite correlation length. So this guy will only be a power law. So this is short range correlation, while the theta is long range correlation. This is Goldstone. Okay, so now let's compute again the correlation function of the longitudinal degrees of freedom. So the delta phi parallel, delta phi parallel. So what do we get from this expression? So this will give you the delta rho, delta rho. So yes, you see, the modulus correlation function is there, plus rho naught square over 4 delta theta square, delta theta square. And I don't have the mixed term because remember, they are uncoupled in the Hamiltonian, right? So the averages uncouple and then the average of delta rho by itself or the average of delta theta by itself are clearly 0. So this is the trick. This guy here goes like e to the minus rho over psi rho. So this guy here, on the other hand, will go like 1 over r to some other power. So let's say r to the gamma, because it's not the same power as delta theta, because there are these funny squares, fine. But if I build averages of fields which are massless, no matter what is the power, I will still get a massless correlation function. I cannot build a mass out of nothing. I cannot build a non-zero correlation length out of nothing. So you see, yes, you do have that the longitudinal correlation length, sorry, the longitudinal correlation function is proportional to the modulus correlation function. But this guy decays faster. Faster than what? Faster than this other guy. And so this is why, asymptotically, if you are looking at the system over large distances, which is what you always would like to do, the C of R will be completely dominated by the second order term. So it will be 1 over r to the gamma. And this is why the overall psi longitudinal is equal to infinity. So simply, you're summing two signals. One which is very much short range, right? Which is the C of rho, plus another one which is very much long range, the C of theta. And the sum of the two is dominated by the long range one, no matter how large is the amplitude. So this is why you have this very non-intuitive result, because yes, the longitudinal fluctuations are almost the same as the modulus fluctuation, but their correlation functions are not. Okay. I gave you diagrammatic arguments. I gave you the geometric argument. And everything I've written up to now is due to the very nice works of Wallace, Brezan, and Wilson in the early 70s. Okay, they did some amazing work on the longitudinal susceptibility, and at the end of the day, it was actually measured experimentally. And so the relation chi longitudinal equal chi perp to 1/2 was really checked experimentally with very careful experiment. Now, at the same time, there were other people doing exactly the same thing in the Soviet bloc. Okay, two guys called Patashinsky, Prokhovsky. Well, I don't remember the spelling here. I apologize for that. They are the authors also of a very beautiful book, Theory of Fluctuation in Critical Phenomena or in Phase Transitions. They were, at the time, they were doing papers exactly in parallel as Wallace, Brezan, and Wilson, finding the same result, finding exactly the same result. Okay. However, I think they had an explanation of this result, which is so beautiful and abstract, which I want to use this last half an hour to give it to you. I think that is a really marvelous explanation, and it is not so well known, so I want to give it to you. Okay, so let's go through the Soviet way to describe everything we've seen up to now. Okay. So what they say is the following. Let's go back for a moment to discrete symmetry breaking. So Ising, right? To fix ideas, let's think of the Ising model. And let's plot the order parameter, so the average of phi, as a function of an external field. So above the critical temperature, so for T larger than Tc, this curve is something smooth of this kind, okay? So you have no spontaneous magnetization, so the spontaneous magnetization is proportional to the field, and it is zero when the field is zero. Then you have the case at Tc, exactly at criticality. So we know that this is the point where you develop an infinite slope exactly at zero, okay? So this is phi, and this is h. So here now, the susceptibility, which I remember is just the derivative of phi with respect to h, it's infinity, right? So you have a critical phenomenon, you have a diverging susceptibility and a diverging correlation length. Now what happens below the phase transition? So in the symmetry broken phase, but of a discrete symmetry, so T smaller than Tc. Well, we know that the curve is something like that. It rise here, there is a metastable branch, an unstable branch, and then it surfaces out here. So let me use colors here. So the blue, this part here is the metastable branch. The red is the unstable branch of the curve. Okay. So you have several notable values here. So first of all, this value here of the order parameter that you reach is our phi naught, is the spontaneously broken value of the order parameter. So this is phi and this is h. And you reach that at h equal to 0. So h equal to 0 here is, if you want, is the critical field of a first order phase transition. This value of the field here is the spinodal value, is the end of the metastable line, okay? So the blue is the metastable line. Well, of course, this was not created by Patachinsky and Pokrovsky. This was very well known at the time, right? So they're using this as a guideline. Okay. So the important point here is the following, that at h equal to 0, so at h equal to 0, chi, the slope of this curve, is finite. While at the spinodal field, so here, at this point here, the slope is infinite. So let's write this better down here. So at h, at h equal to its critical value, that is 0, the derivative of phi with respect to h is equal to chi and is finite. Okay. However, at h equal to the spinodal value, the slope of phi, okay, is infinite. So why is that? Well, if you want to have a potential representation of this result, well, what is going on is the following. When you are at zero field, so at the critical field, you are at coexistence, right? So you are in this situation. The potential is something like that. So this is what happens at h equal to 0. So here, to go to the other side, you must push. And if you push gently your state, you will change a little bit the magnetization. So this is why you can go across the first order phase transition and nothing particularly spectacular happens. So you can pull up the state, okay, because the potential really exert a resistance. So this is why chi here is finite, right? It's just a curvature there. On the other hand, at the spinodal value of the field, what you have is something like that. So this is what happens at the spinodal value. Now, really, you have no resistance of the state to roll down to the stable one. And this is why chi spinodal it's equal to infinity. And again, this was very well known. So, but the bottom line here is that you have these two different values of the field, these two different positions in phase space, right? At h equal to 0, at the transition field, you have a finite susceptibility. At the spinodal field, you have an infinite susceptibility, okay? So the bottom line here is that the transition field HC equal to 0 is different from the spinodal field, H spinodal, and here chi is different from infinity, while here chi spinodal it's equal to infinity. So let's say smaller than different, sounds weird. Okay, so this is the normal scenario of second order and first order phase transition, because here we are describing both, right? So this is the first order phase, sorry, this one here is a second order phase transition in the temperature, while this one here is a first order phase transition in the field. And I hope you have the background to understand this, because this is standard critical phenomenon. Now, Patashevsky and Pokrovsky says, okay, let's try to generalize this scenario to the case of continuous symmetry breaking. So what do we expect from the case of continuous symmetry breaking? So at large temperature, above the phase transition, we'll have the same kind of behavior. Now let's be careful. What do we have on our axis? This is just a scalar plot. So let's put here the modulus of the field, and let's put here the modulus of the order parameter. Okay, so this is what happens at t larger than tc. At tc, okay, again, we will have a critical phenomenon. So this will get infinite slope here. So modulus of average phi, modulus of the field. Okay, so this is what happens exactly at tc. And so here, unsurprisingly, you have always an infinite susceptibility because you are the critical phenomenon. Now, the great question that they ask is, what happens below tc, in the symmetry broken phase? Well, this is tricky, you know, because, so this is the field, the modulus of the field, and this is the modulus of the order parameter. Because we know that there will be a spontaneous non-zero value of the order parameter. Let's call it phi naught. Okay, so you are below the transition. You must have a non-zero order parameter even at zero field. So this is the symmetry breaking. So could it be something like the Ising model? So is it possible that there is something like that? and so on and so forth. So this is hypothetical. So this is the question I'm asking you. So if this is the case, we would still have that the critical field HC, which is equal to 0, would be different from the spinodal field. So you will have the spinodal field different from the critical field. But does this make any sense? So remember, the interpretation of this was that when you have zero field, if you add some extra field, you can climb up the potential, right? So you can push a little bit the ball up over the potential. So this is why in the normal case, you can go beyond this point because you can create some different, some smaller order parameter by adding a field. Is this reasonable in this case? Well, let us remember what is the shape of our potential now. In the case of a continuous symmetry. So now our system is here, spontaneously broken symmetry. So this is the value of our phi naught. And now you ask yourself, can I decrease the value of the modulus of phi naught by adding a field in this direction? So in other words, can I make the system actually climb up along this direction? No, you can't. You can't, because if you put that field, what will happen is the system will just go around and it will go on the other side to align to the field. So the system is totally, utterly unstable against adding even a very small field in the opposite direction. So the red paradigm here cannot be the right one. You cannot climb uphill when you have a very comfortable and cozy zero mode around which to circle, right? So if we plot that from above, so this is a line of minima, all with the same energy. So here you are, value of phi naught at h equal to 0. So now what you're asking is, okay, if now I put a field in this direction here, will I push a little bit my system in this direction? Not at all. It's impossible. What the system will do is just to roll along the marginal manifold, the zero mode manifold, to align to the field. I find that the simplicity of this argument is really staggering. So what they say was, okay, so this means that the critical field, h equal to 0, must be the same as the spinodal field. So it's not the blue, it's not it's not the red line, the true thing, okay? So let's leave the red line there as a reference. What will happen is that the curve will arrive to phi naught with infinite slope and then go back in a non-physical region. So all this is the non-physical region. So they conclude that the value of the critical field is the same as the value of the spinodal field, okay? And this is why, because of that, so because H critical is equal to H spinodal, then chi, the longitudinal chi, is actually a spinodal chi, and then it must be infinite. Amazingly, by using this argument, they're also able to describe the kind of divergence here, and they find the right exponent. And they find, okay, so from that, they really find also that chi longitudinal must be equal to chi perp to 1/2 in 3 dimensions, which I think is nice. it's a very, very nice argument. Okay. So let me go back now Flock to draw my final conclusion about spontaneous symmetry breaking of a continuous symmetry. But don't forget this. This is nice. Okay, so finally back to Flock for the last time. Well, so back to Flocks. So the rotational symmetry is continuous and it is spontaneously broken in Flock. No doubts about that. So we expect from standard physical argument that the correlation length of the velocity is proportional to the correlation length of the transverse mode, which is infinite. And so we expect from Goldstone that psi v is scale-free. So this is not surprising at all. However, we also expect, so this is, let's say, from theory. We also expect from theory that the psi of the speed is the modulus of the degrees of freedom. So it should go like psi of rho. So this is the speed, and this is the modulus. Remember, we didn't compute the longitudinal correlations after all. We really computed the speed correlation, the speed fluctuation. So this is small, must be smaller than infinity in the theory, right? And so one should find a speed correlation length that is constant. Maybe large, but constant. So all this is what comes finally from the theory. And now, what comes from the biological experiment? So experiments. But from experiments, as we know, we got that psi v is indeed scale-free, right? So this is as good as theory. So the theory predicts linear, okay, fine. So biology is the dots. So this is biology. The red line is physics. And they agree with each other, so fine, agreement. On the other hand, the correlation length of the speed fluctuations data show also a linear scaling. So data bio show linear scaling, while after all this theory, which was quite a bit, physics is telling us that this should just be constant. So we finally can say that the correlation length of the speed fluctuations, not any correlation length, the correlation length of the speed fluctuation, not the one of the velocity, not the transverse one, and not even the longitudinal one, but the correlation length of the speed fluctuation is not as standard theoretical physics would predict it to be. So speed fluctuations biological are not as standard field theory predict them to be. So after all, finally, we do have something original, unexpected or surprising, which is not merely written in the DNA of spontaneous symmetry breaking. So maybe it is written in the DNA of birds after all. Okay. And the next time we'll see that, how then we have to change the theory by adding some new extra ingredient to comply with the biological result. But we will still do theory at the physical level, but with some new extra ingredients. So it will no longer be the standard theory. But for now, let me focus your attention on how much standard equilibrium and yet, well, I would say, in my opinion, highly non-trivial physics we had to go through simply to understand what there was to be understood at the biological level. So that was a lot of stuff. And apart from this specific case, this was really what I wanted to be the main message of my lectures. I feel that sometimes we give up physics, even standard physics, too quickly. So in front of the dazzling diversity and variety of biology, which is always fiercely out of equilibrium and strange and so on, we're tempted to immediately throw away decades of quite solid theoretical physics. But physics too, in my opinion, may be rather dazzling sometimes, with many unexpected turns like here. So first we were surprised, and then, okay, no, there is Goldstone, so we're not surprised, okay, but then there is a longitudinal mode, okay, so we are surprised again, oh no, the longitudinal mode is also massive, so we're not surprised, oh, but the modulus is massive, so we go back being surprised. So a lot of turns. So the fact that these turns have been explored, I don't know, 50 or so years ago, as in the case of what I told you today and the other day. So this is 1970s physics. I don't think is a good reason to overlook this argument. Okay, today I can stop here and collect questions if there are questions.
Okay, question? As yesterday, if you have a question, you can come here to ask Andrea. No? All right. No questions today. There will be a lot of questions maybe tonight. I will think about them.
Okay.
Okay.
9 o'clock.
Thank you very much, Andrea.
Okay.
So see you 9 o'clock. Yes, 9 p.m.
Okay. Bye-bye.
Bye-bye.
Bye-bye. Have a good one.